All right, well, good morning or good afternoon, everyone, and welcome to today's Engineering Management Institute sponsored webinar. Today's webinar is sponsored by Schnabel. We're thrilled to have Douglas Genevin with us today, and he's going to be giving the presentation, and I'll hand it over to him in just a minute. But before I do that, I do want to welcome all of you for taking some time and spending it here with us today. And I will just say at the Engineering Management Institute, we put a big emphasis on helping engineering professionals become better managers and leaders. And we do that through a lot of our content that is free and available to engineering professionals, like our podcast, our YouTube channels, and these types of webinars. And it's only because of companies like Schnabel that we are able to do things like this. So we're thrilled to have them as a partner and a sponsor in this session. And they've done some other things with EMI as well. And today's topic is going to be the Cal Poly Fremont Hall landslide stabilization. This was a landslide occurred on the California Polytechnic State University, San Luis Obispo campus in February 2017 during a period of heavy precipitation. And again, I'll let Doug give the backstory in a minute when I hand it over to him. But just real quick, I do want to introduce Doug Genevin. Doug is a licensed professional engineer. He's currently the operations manager with Schnabel in Walnut Creek, California, where his responsibilities include overseeing the design and construction of specialty earth retention and foundation projects in the far west region. Doug joined Schnabel in 2000 after spending 9 years in the geotechnical consulting business as a senior engineer and laboratory director, working on projects in the mining, earth retention, and landfill sectors across the United States as well as internationally. So with that, I'm going to turn this one over to Doug and let him take us through the Cal Poly Fremont Hall landslide stabilization. Doug?
Thanks, Anthony, for the introduction, and welcome everyone today to the presentation. We are going to be talking about the stabilization, the landslide stabilization project we did at the Cal Poly University in San Luis Obispo a couple years ago. So this course, again, qualifies you to receive one PDH for your time today. So after we're finished, you'll get some instructions from Anthony on how to complete the certificate and whatnot. So make sure you stick around for that and get the instructions.
Hey, Doug, just real quick, I should have mentioned that. Thanks for mentioning it. I do have the survey link, and I will be putting it in the chat when we get to the Q&A today, which you'll need to fill out to get the survey, to get the PDH. So thank you, Doug, for that.
Okay, so today, kind of review some of our learning objectives for today. So today, we're going to learn about what we've termed the collaborative design build process for this project deliverable with this broad scope of landslide stabilization. We're going to also see how we can qualitatively use these in the evaluation of risk assessment can be used for these stabilization solutions. And we understand some more of the design considerations required for the investigation and stabilization of these designs. We want to also learn some of the technical challenges that we had to overcome that are inherent to these landslide stabilization projects. And finally, see how bounding some of the design unknowns can lead to an efficiency in the final design and construction costs. So a little background or the outline to the talk today. We're going to give you a background of the project and introduce it to you from a kind of historic standpoint, and also then move on to the different phases that we worked on in this project. The first phase was the evaluation, characterization, design, where we worked through alternative evaluations, performed the investigation and design, and then worked on construction cost development. And the second phase of it was the actual construction of the project itself, and it was, the fruition of the first phase of the project. So in February of 2017, as Anthony was saying, we had a very wet year out here, wet winter. And all of that precipitation caused a landslide to activate and come down, contacting one of the dormitories on Cal Poly San Luis Obispo's campus. This is Fremont Hall Dormitory, and with it, it caused the necessity to evacuate about 270 students all total they had to be relocated to other spots on campus and then off campus as well. So in the interim, while they were working on a design solution for this, the dorm remained unoccupied. So kind of a scale, you saw it close up from behind the project here. This is Fremont Hall, but the major scarps that were visible in the features were shown there in red, and then the approximate landslide boundary extended clear up the hill. So, as we said, this, in 2017, we had this landslide activate, and then between 2017 and 2019, the university performed some preliminary characterization programs and a couple of small remedial construction efforts to try to prevent further damage to the hall based on further slope movements. The remedial construction efforts weren't completely effective, and in 2019 the slide reactivated again and brought more debris down against the dormitory. So at that point the university decided that it was time to change course, and they needed to develop a more specific and focused site characterization program for the landslide, and it was estimated to be larger than what they could just issue as a standard change order. So they came up with a request for proposals that involved both the characterization of the landslide as well as a remedial design that would be performed by a specialty design build contracting team, which would eliminate issues of constructability and scope gap that they had seen in some of the preliminary remedial designs that they came up with. So this came out to bid in July of 2019, and we were awarded the work in October of 2019. So the project's referred to, or the official name of it was Fremont Hall Landslide Collaborative Design Build Project. Now, we are probably familiar with some of the mechanisms for project deliverables. We have got the classic design bid build project, which we all know of, the design build projects, which would be, owner hires an engineer and takes a design to 20 to 30% and then produces a set of method specifications of which design build teams then bid off of, and then finish the design and then construct a project. The CSU system, the California State University system, had done numerous design build projects through time, but they felt that some of these projects didn't always achieve the goal of what the university really was looking for from the outcome of the project. So they developed this method of deliverable called the collaborative design build, which inserted more input and interaction between the owner, which would be in this case Cal Poly, and the contractor slash designers, in order to produce a design that was really what the university wanted at the end of the time. So that's the name. This is one of, I think it was the second one that was done on campus here, and the first major facilities project that was done. So this project was designed or developed or kind of composed into two phases. The first phase was involved in an alternatives evaluation, where several design alternatives were to be evaluated and scoped out. Then the characterization of both the geologic and geotechnical characteristics of the site were to be done. And of course, the remedial design of the chosen alternative was to be taken to completion, and then construction cost estimating was to be done. So the university had a sound cost of what the project was going to run them. The second phase of it then would be construction of the remedial solution. So Schnabel, we teamed up with Yeh and Associates as the geotechnical engineer of record, and Cannon Engineers as the civil engineer. And we were awarded the contract as the design build team leader and general contractor for the work. Our role was to do obviously the general contracting work, and then the geostructural design and construction. Yeh was to be the geotechnical engineers and geologic engineers of record, and Cannon was to be the civil engineer of record, designing all of the civil features and drainage and earthworks. So the first part of this was coming up with the alternatives of the investigation in the investigation work. The alternatives analysis and preliminary pricing was to evaluate several potential remedial designs with rough orders of magnitude pricing to it. The second phase again was to obtain new topographic survey data, which the data that was existing was old and obviously a lot of movement had happened in between the current time frame in 2019 and before, to nail down a quantitative characterization of the extents and limits of the 2017 landslide, and then investigate a couple of outstanding questions of whether there was a deep-seated landslide potentially in play here, and then a potential for debris flow hazards coming down the slope to the dormitory. And then once the selected preferred alternative was reached, then to prepare the construction plans and specifications to complete that design. And finally, the costing of it was we were to produce a guaranteed maximum price for the remedial solution. And then if that was acceptable to the university, then we move on to phase two, which would be the construction portion. So the alternatives evaluation. So 5 alternatives were selected for evaluation based on the effectiveness of the concept, how constructible they were, impact to the campus, and of course, cost played into that quite a bit as well. So of the 5 choices or the 5 alternatives that were examined was a simple earthen buttress constructed with imported fill at the base of the slide. Deep soil mixing, where we would stabilize the slide mass in place using deep soil mixing techniques. A cantilevered pile wall design, which would be a drilled shaft design. A tieback soldier pile wall, which would be a single soldier pile wall at the toe of the slide that would stabilize the mass in itself. And then a tieback soldier pile wall at the toe, but the inclusion of uphill galleries of anchors to help facilitate the stabilization. So the earthen buttress approach was fairly straightforward. It would be the removal of the slide mass at the base and then the construction of a structural fill buttress at the bottom. It's a proven technique that's been done before. It's a passive solution. It doesn't require a lot of technology to get it completed, but had some significant disadvantages to it where digging out the toe of a landslide has the potential to activate even a larger portion of the landslide. A large quantity of fill was estimated to be about 60,000 yards that would have to be hauled off and then brought back in. So the campus impacts of the trucking of that soil in and out of campus was seen as being a significant impact. The next potential alternative would be a deep soil mixed earthen buttress, where we would, using soil mixing techniques, we would stabilize the mass in place, making it stronger by the inclusion of cement mixing with the soils, the on-site soils or the landslide soils, to create a more stable mass. This had the advantage as we weren't importing any soil to do the work. There's a passive solution as well, to stabilize things in place. But it had limitations with regards to stability of the benches that we'd have to be working on. The production of large quantities of spoils that would have to be disposed of. And then obviously the trucking of the cement on site in order to do the soil mixing was seen as quite significant. The next would be a cantilevered pile wall, which would be a series of cantilevered drilled shafts. Reinforced drilled shafts would be installed at locations within the slide mass to stabilize it. This again was a proven solution, had worked before in previous stabilization routines or plans, but it was anticipated that the embedment of these piles would need to extend into the sandstone and native bedrock below, which was known to be very hard. And so drilling 40 to 60 feet into the rock, we knew was going to have a very high quantity of cost associated with it. This also doesn't address any of the upslope potential movements of infrastructure in regards to long-term creep and other issues that would entail from that. Next would be a single tieback wall. This would be a stabilizing wall constructed at the toe of the landslide. It would allow for the regaining of this courtyard area below, as you'd be able to install the soldier piles with the anchors and then re-excavate out this slide mass between the dorm and the wall, which was one of the goals of the university. It is an active solution, so you can apply great amounts of force to this wall to stabilize the slide. But it's a single wall solution, and the potential for upslope movements still existed due to the existing grading that was at the site currently. Also, the forces to resist these loads was going to be significant. Lastly was the tieback wall, like we showed before, but smaller of capacity, and then the inclusion of upslope galleries of anchors. This idea facilitated to be able to construct it from the top down by stabilizing the slide in place. We could also incorporate subsurface drainage with the inclusion of some horizontal drains, and it reduced kind of the long-term creep issues of the slide mass above the soldier pile wall. Disadvantages to this would be if the grading plan couldn't be accommodated, then some of these galleries would remain exposed and be visible on the hill after construction. So with all of these alternatives kind of thought through, we put them into a matrix, and we're able to sort of grade them on 5 or 6 items here. The reliability of the design, how constructible the design was, how weather impacted the alternative was, if it had a high carbon footprint, and then the impact to the campus. This was a big factor for the university because the school is there for the students, and impacting operations of the campus was of high concern. And of course, the cost of the items. So the items were graded kind of good to bad, and with the red being bad, the green being good. And you can see we sort of just ended up stepping through the matrix and then arriving at the best solution was the tieback wall with the upper anchors and galleries. So with that collaboratively agreed upon, we were able to move forward into the design and investigation portion. And we talked about this being a collaborative process. Part of this collaboration was the university had hired a geotechnical consultant that would serve as a peer review and validator of our conclusions and premises that we were going forward with. They were an experienced landslide geotechnical and geologic consulting company. And so we had to collaboratively agree on some of the conclusions, and they mainly focused on this presence or no presence of this deep-seated landslide, the potential debris flow hazards that existed, and then really agreeing upon the full limits of the 2017 landslide. Kind of secondarily, we would need to come to a collaborative agreement on the strength parameters and seismic design considerations for the project. These, I think, were probably easier. These were, had more speculation or more subjectivity to them. So, as they say, the definition of entropy is once something is said, it's hard to take it back, right? Or once the toothpaste is out of the tube, you can't put it back inside. So back in 1975, Hall and Pryor had mapped a fairly large extent of a landslide debris fan that spilled out into the campus proper. Now, the red arrow is pointing to our Fremont Hall here, but you can see that it extends way out into the original dormitories here, as well as the rest of the red brick dorms, which is Fremont possibly, and even into some of the other campus buildings. So this was where this, the presence of this deep-seated landslide, did it really exist, and was it to this great extent? subsequent USGS geologic mapping that came up, kept the landslide identified as kind of what it had with Holland prior. This is, in 2004. You can see lots more buildings have been constructed inside of it. We have another set of dorms here, the Sierra Madre dorms, Yosemite dorms, that were potentially in this landslide fan. Vigers in 2010 kind of changed the mapping a bit, and what we've come to the conclusion, or we'll go through later, but it was limited more to just being right to the extent of Fremont Hall and then to either side of it. So this was kind of where it sat in 2010. So again, from a perspective standpoint, we have our Fremont Hall here. We have our kind of approximate map of the landslide from 2017. The Holland prior extent would have been something to this effect and had far more far-reaching consequences to the university. As you can see, other dormitories are involved, significant infrastructure. This is a reservoir number 4. The beloved Cal Poly P would be in danger of sliding down the hill. So this was a major concern of the project to investigate this and either conclusively rule it in or out of the issues. So Ye Associates did a very good job of going back through the archives at the university and finding a lot of photographic evidence of the campus throughout its development over time. And you can see here, these were the original dormitories that were constructed on site. Here is reservoir number 1. We'll notice this for reference later on. Here's the Cal Poly P up on top of the hill. And here is this debris, this landslide debris fan that kind of extends out into present day campus at the time, but it was at this point undeveloped. Here's a kind of a closer up view. This is kind of a limit of where that fan existed and where Cal Poly or the Fremont dorm would eventually sit, reservoir number 1 and P. So this is a shot during November of 1959 during the construction of it. There's obviously evidence of a mapped landslide, historic landslide mapped here. And so part of the construction of the dorm, involved the things that we really don't want to do, right? They dig out the toe of the landslide. In this case, they then took the fill and put it up on top of where the scarp of the landslide was. So they cut out the stabilizing buttressing effect to the bottom of it and then actually loaded up the top of the landslide, which would eventually come to bear with us. You can see the haul road up to where they're placing the material. Here again is reservoir number 1, and there's our Cal Poly P. So in 1960, here's a few years later, you can see the back cut to facilitate the construction of Fremont Hall. You can see the fill in place now from the excavation efforts. Here's reservoir number 1. Here's the P. You can see this was the extent of where the Holland prior landslide debris fan extended out to. Again, in the mid-60s, you can see this zone here. So in 1962, I believe, this back cut, the dorm experienced a minor instability where it had a small landslide pop out in this corner here. And as a result, they flattened out the slope behind the dorm some to its present day situation. You can see it here in 64. And then in 1975, you can see how it's flatter. And this is then again the mapped zone of it. But this all area here has been largely removed and development of other facilities have been put on top of it. So as part of the characterization plan, we needed to Ye Associates went through all of the massive amount of geotechnical and geologic information that had already existed. And then we also did some additional coring ourselves. We cored 5 rotary wash corings for more borings that we were able to continuously log the core through the landslide mass. and find the shear plane for it. They were up to 150 feet in depth, as well as drilling deep enough to potentially look for this deep-seated landslide that was potentially there. Ye and Associates also did 4 bucket augers, which were 24-inch diameter open hole shafts that were able to allow a geologist to go down and map the landslide mass itself. You can see here's a photograph, up close photograph here, 46 feet below ground. You can see that there's the shear plane of the landslide, and it's only about 6 inches in thickness that whole slide was moving across. These bucket auger borings proved to be very, very important, very conclusive. Ye and Associates also did a number of test trenches along the outskirts of the landslide to determine the limits of it. And so then combining all of the existing data plus the information that we obtained. So there's our additional 5 corings, 5 rotary wash corings that we did. These are our 5 bucket auger work that we did. And then the test pits for the extents along the sides. You're able to then revise a more accurate geologic characterization map. And through this, we were able to find that the 2017 landslide was limited to this orange area here. The previously mapped Hall and Pryor 1975 zone, this area here, the landslide deposit was largely removed by the university development. So there was nothing actually built on this any longer. It was limited just to the material behind Fremont Hall. So from there, they're able to develop their cross sections, and they found this massive Greywacky sandstone block below Fremont Hall, of which it was founded on, and then the landslide mass moving over a shear zone between that contact of the slide debris and the parent bedrock material. So from the investigation conclusions, we were able to find, conclusively come to agreement that the landslide, the earth flow landslide have occurred, pre-Cal Poly history, as well as in 1962, 2017, and 19, and it is occurring over a shear zone that's at the contact between the Franciscan, Melange, and Greywacky material and the shear zone. The previously mapped larger landslide deposits have been mostly removed by campus development, with the exception of what would be east of Fremont Hall or uphill of Fremont Hall. The deep corings gave conclusive evidence that there was not a deep-seated landslide present. And through literature studies, they'd seen storms and earthquakes, other geologic hazard events that had produced no indication of a deep-seated slide reactivation or activation at all. There was an extensive Greywacky sandstone block below the Fremont Hall structure, and the buildings that were supposedly in this fan of that was previously mapped of the landslide haven't reported any or observed any movement of the structures or distress. So it was pretty inconsistent with any sort of deep-seated landslide, and the group was collaboratively able to come to that agreement that all we were dealing with was the 2017 landslide above the dormitory. So with that behind us, now we're able to work on the design of the landslide remediation, which was the tieback galleries upslope and the soldier pile wall at the toe of the slide. So that involved coming up with a geometry for the galleries, tieback anchor loads and spacing, and then of course the structural whale design. So now that we had the limits of the landslide defined, it was now a matter of working through a grading plan that would allow us to get a sequence of galleries that would stretch across the width of the slide to provide the stabilizing forces to it. 3 cross sections were developed through that to accomplish this. And from there, we were able to then develop cross sections, which allowed us to then place on here the mapped shear zone of the landslide, and then determine the geometry of the subsequent wales and soldier pile wall, and determine the unbonded lengths of the tiebacks in order to get through the landslide and anchoring into stable bedrock material below the landslide. So with that, Ye and Associates did a fair amount of stability analysis to determine kind of the global constraints of it, and then Schnabel revised or fine-tuned that analysis to tweak the geometry and loading of the anchors to perform the geotechnical or the geostructural design from that case. We then designed the concrete wales that the tieback anchors would be installed through and tensioned against. And they were roughly 24 to 28 inches in thickness and 8 to 10 inches in back height. Or 8 to 10 feet in back height, sorry. So with those designed and worked through, we then had to come up with the soldier pile wall design, which included both layout and geometry to make sure that the stabilization forces were perpendicular to the direction of the slide mass. Again, determine the anchor loads and then design a permanent facing for the wall solution. So the soldier pile wall was designed into kind of using uniform pressure distributions based on the static landslide stabilization forces and then the seismic contribution. Once again, these were then the toe of these soldier piles were founded within the sound bedrock, the Greywacke sandstone below the slide, anchoring it at that point. We also then were able to determine the required unbonded lengths of these anchors to make sure that we were below the landslide. So with the layout complete, we then were able to specify the directions of where the tiebacks had to be directed to provide those stabilizing forces and incorporate the geometry of the wall that was able to regain this area loss, this courtyard area loss from the slide mass that came up against the building wall of the dorm during construction or during the landslide event. So the elevation view, see the contact of the slide plane that we showed you. So with the design work finished, we then were required to come up with a cost for this remedial solution, right? The $64 question, right? So we produced a guaranteed maximum price for this remedial solution as the general contractor. Those costs needed to include obviously the geostructural repair work, the galleries and the soldier pile wall, but also had to include all of the earthwork, both the temporary and final grading work. There was a significant amount of temporary grading that had to be done in order to facilitate the construction of the benches to get access to the work. And then the final grading to level the slopes off to be flatter than 3-to-1 slopes so that we wouldn't have continued minor slope movement afterwards. Stormwater control and drainage was a big part of draining the surface water off the slide. Revegetation, landscaping and flat work in the courtyard area, and then the permanent fencing that would be the enclosure for the landslide site. So with all that done, the GMP was submitted to the university, and this, of course, we were awarded the project in October 2019, and then we all, by February, everything was kind of working remotely due to the COVID pandemic. We worked through most of 2020, and then we were able to go to construction in the summer, kind of late summer, early fall of October 2021. Is that right? Yeah, 2020. So the construction sequence was important, phasing the construction so that we would build the work from the top down so as not to destabilize the landslide while we were trying to construct the work. The soldier pile wall and anchors, we had to construct a bench to build that work from down below. And then we had horizontal drains and a landslide monitoring program that needed to be installed as part of the construction process. So starting with the concrete well and tieback construction work. As we talked about before, there was a sequence of nominally 4 rows of galleries, but they had to be built in stages so that they could minimize the amount of temporary grading that would be done at the site and still get a full stabilization force across the width of the slide. So we started at gallery 4 and worked our way down in sequence across the landslide while constructing a bench here at the bottom in a berm to work off of the tieback, the soldier pile wall at the bottom. So for the tieback whale construction, it began with the temporary grading where we got to our bench location, and we cut in our back slope for our whale. From there, we finished digging the trench that would be the bottom part of the whale. Once that was completed, then we were able to follow it up with the tying of the reinforcing steel for the whales, shotcreting the whale in place. And then we backfilled the trench to give us access back up to the whale where the blockouts were. We then further install our tiebacks. Once the tiebacks were installed, we were able to test them and lock them off. And they were finished with cutting the strands off, putting galvanized caps on it, grouting the caps off. And then depending on where we were, these were the grading plan called for potentially either leaving them exposed where a permanent facing was applied to it, or they were just buried in place. And when it's all said and done, this is an aerial shot of the final grading happening. You can see that galleries 4 and 3 are completely buried. Gallery 2A here is partially exposed. 2B or 1B is partially exposed here. Gallery 1A is largely exposed down here. I have a shot from a different angle. You can see that we're able to basically minimize the exposure of these by working with the grading plan to cover them up. Okay, so moving on into the soldier pile wall construction sequence. This was one of the challenging portions of the slide. We knew that, from previous experience with what happened in 2019 with the reactivation of the slide, we couldn't just dig out this slide mass at the bottom. We had to construct a berm that we could work off of. It would serve as a stabilization, keep the landslide stabilized from reactivating, but also give us a bench to work on. So we constructed a bench at the bottom, which allowed us to be able to get the soldier pile drill rig up on top, install the soldier piles, see angling them in the direction of the landslide mass. We then, once the piles were installed, we were able to excavate down, lagging to tie grade, installing tiebacks, testing, and repeating the sequence where there's multiple rows of tiebacks in this. You see some of the area exposed bedrock material above the slide or below the slide mass. Others had lagging all the way down to the bottom. I guess the work progressed. And finally, once we reached subgrade with the tiebacks installed, we were able to then install the drainage material, the drainage board behind the walls. We came in and we installed our horizontal drains into the slide mass to drain it. Tied our reinforcing steel. Constructed our permanent facing for the wall. And then the permanent facing was in an architectural sculpted finish was put on it and was stained to give it a natural finish to it. You can see here the completion of our work, but the grading work was still going on. You can see the extent of the wall, which regained the courtyard area behind the dormitory, which was one of the key features of the university's goal. Basically shields now the entire dorm from the landslide mass. And then once the landscaping and flat work was completed in the old courtyard area, it produced a very nice area for the students to enjoy an outdoor recreation area, along with barbecue pits and some seating areas and some lawn area. Okay. So other aspects that were involved, I mean, managing groundwater within the slide mass is key to a successful remediation program. And in doing so, we designed horizontal drains that would passively drain the slide mass with the goal intended to keep the water table down off of the slide plane. These consisted of drains installed up at Gallery 4, which intercepted water coming into the slide, as well as drains that were installed through the soldier pile wall, which you saw in the previous photographs. Drains ranged from 75 to 100 feet in length and tapped into that, if you want to say, the basin of material, the slide mass material just above this dormitory area. We also installed 5 vibrating wire piezometers within the slide mass to monitor the water levels within the slide. There's a plan view of, you can see the drains installed through the soldier pile wall, the drains installed up at Gallery 4. They were simple design. They were just drilled through the slide mass into the competent bedrock below, allowed for drainage off of this sheer slide boundary. The vibrating wire piezometers, 5 were installed. We had 4 within the slide mass itself and 1 above the slide mass by the reservoir number 3 to monitor groundwater levels. They also were equipped with data loggers so they could record things over time. Oh, in addition to the drains and piezometers, we also had a physical monitoring of the slide for movement during the construction projects, and it would be implemented long term. So we performed weekly survey readings on reflector targets on the concrete whales. From those, we also did monthly readings of the inclinometers that were installed as part of the characterization program. And again, monthly readings of the groundwater levels and discharges. That was from a drain upslope of our work. And then we instrumented tiebacks to monitor loads, and those were monitored during construction as well. So the physical surveying monitoring program, we again collected information off of survey targets, reduced the data into horizontal and vertical deformations of the whales. Those weekly readings were put in the data reports, where we were able to develop and interpret movements and basically verify that the predicted behavior was as what we were expecting, and also to watch for anything compared to our predicted results. And then it was also a means of validating our design assumptions, our loads that we had concluded from our design portion. So you can see we had a significant number of survey locations at each of the whales and at the soldier piles, and then produced graphs over time. So you could see positive readings were displacements downhill, negative readings were displacements uphill. So you can see after the whale was constructed, we saw some downhill movement from relaxation of the slide, the destabilization of it. And once the anchors were stressed and locked off, the whale was pulled back into the slope slightly, and then we maintained a stable movement. So inclinometer and water level readings were made monthly by Yang Associates as part of the construction contract. We didn't see much movement within the inclinometers during construction. Any appreciable movement that was observed was attributed later on after construction was completed, with rises and falls in water levels associated with storm events. And this justified the long-term monitoring plan of the water levels within the slide mass. So you'll see during our work, we only had about 1/8 of an inch of movement downslope. And the water level stayed pretty consistent during our work. We were lucky to go, construction started in October, which is not kind of the ideal time to start a landslide remediation project, but we were fortunate that we didn't have a lot of significant rain events during our construction work. There's also a drain that was installed as part of a previous project. Flow rates from this were also monitored for changes during the construction. So tiebacks, 11 of the tiebacks were in the gallery were instrumented, and 4 soldier pile tiebacks were instrumented. These were done using the DSI Dynaforce monitors, baseline during the testing process, and then monitored for long-term performance over time. What we were able to see was that the loads came up and reached design loads as expected, and then stayed constant over time. So we knew that there wasn't continued creep movement of the landslide that was causing the design loads to rise on those whales. Yay has now a 5-year contract to do quarterly monitoring of the landslide, and everything is proven to stay relatively constant. Okay, so in summary, the collaborative design build project model resulted in a successful and timely repair of what would be a significant landslide at a very critical facility. The process of combining the characterization of the landslide with the design of the remedial solution produced a design that went to construction that was very constructible, well planned and executed, and actually resulted in no design related change orders to the owners. So this method, what was priced to begin with actually, ended up being exactly what it cost to do the work. In fact, actually we had actually some cost savings on the job, which reduced the pricing. The analysis of the ongoing monitoring has shown the effectiveness of this design, even during these subsequent severe storm events that happened in winters following this, where the groundwater table rose within the slide, but then subsequently drained rather quickly due to the horizontal drains. So some acknowledgements. We want to acknowledge the university itself, Cal Poly, the facilities department, Anthony Palazzo and Michelle Sharderson. Dr. Rob Moss, who was actually on our team, served as a peer reviewer and collaborator with the characterization. Yay and Associates, obviously, from their work with the geotechnical characterization, Judd, Jamie, and Gresh, and the folks at Cannon, Pete, leading the civil team, and then Burrow, Bob, and Chad with the surveying team, did quite a bit of work for us. So with that, I think we're kind of at the end of the presentation. So I think, Anthony, we're at the point where we can maybe field some questions if you have some.
Okay, great. So once again, thank you to Doug Genevin from Schnabel for being our subject matter expert today and leading us through this interesting presentation. Definitely a lot going on with this project, but it was very interesting. And I'm going to open it up now. And I will put the evaluation. Give me a minute or two. I'm going to pop it in the chat here to fill it out to get your PDH. In the meantime, does anyone have a question for Doug, whether you put it in the chat or you can use the Q&A queue there? Any questions? I see there was a question that came in earlier saying any inclinometer installed during the investigation or construction, which there was. Doug went on to show us that and show us the images of that. So, and you could see the measurements. You'll show that there was very little movement. Any other questions? All right, well, I am going to put my, for now, I'm going to put the chat in so you can grab the survey. Doug, just a question that I had myself in terms of when you're working with a school like that, the communication for the school, how did that work? Was there a contact? Was it through the contacts? I know you mentioned some people. And was there meetings with everybody regularly? What did the project management side look a bit like from communications?
Yeah, so this project was run through the facilities department, which entails both the maintenance and then long-term planning. So we had a project manager and project executive, so to speak, that was with the university that oversaw the project. We worked. He actually has left Cal Poly since then. His name was Eric Soder, and he was our main point of contact that would facilitate coordination. You had facilities was sort of the or it wasn't sort of, it was the point of contact for us, but then you had interested groups of the housing department, parking groups. There's quite a few different groups that were involved with, what they wanted to get out of this project at the end. It's unrelated to us. They took advantage and did some renovations of the interior of Fremont Hall. So there was
Okay.
other facilities groups that were involved with sprinkler systems and things like that we needed to coordinate in and around.
Okay. Here's a good question that came in. It strikes me that this was a very expensive project to regain ground near an old dorm building. Number one, was this necessary to protect other structures? And number two, was there consideration of abandoning the building or replacing it with something else?
Yes, absolutely. There had been a lot of constraint. That's why the initial cost estimating was done uh, for the university's sake. Like I said, we had 217 or 270 students that were in there, which uh, constitutes a significant number of students that the university wasn't able to house. Housing is of shortage, on-campus housing is of shortage, as well as it's a loss of revenue stream for the university. So there was consideration of just eliminating the dorm altogether, but that from a short-term and long-term plan didn't come into or was prohibitive to the long-term gains of keeping it in place.
Was there any risks to other buildings because of this, or was it limited to that area or that building?
Largely, it was contained to Fremont Hall directly.
Okay.
But the other thing of do nothing they would have a landslide that would continue to creep along and continue to spill out into the footprint there if they took down Fremont Hall. So it was still seemed that something needed to be done with the slide.
Okay. Great. One bookkeeping question, I mean, a housekeeping question we're getting is yes, the slides will be available and we're going to put together a recording page with the recording and the survey and stuff. So we'll send that out to everybody. Question though here, Doug, why was shotcrete chosen for the retaining wall and tieback caps instead of traditional concrete?
Ease of construction. With traditional concrete, you'd be one side forming it, which requires formwork and more construction. For these types of walls, it's more cost effective to use shotcrete.
Okay. Another question. The GMP was agreed to at the time of award of the contract or after the finalization of the design solution?
So there was an estimated GMP that was part of the bid package, and it was by and large related on not having all of the information. So prior to
Doug, what is GMP for those not familiar with it?
guaranteed maximum price. So
Okay.
when we did when we finished the finalized design, we came up with what we call a guaranteed maximum price, which was our price to the university all told. And so that was not really able to be finalized until the design was complete. And at that point, then the university agreed to that and then awarded the contract based on that.
Okay. Excellent. All right. Well, I think Doug answered all of our questions, gave us some great information today. I want to say thank you again. One more question here. How much silicate did they use?
Silicate in regards to what?
In regards to what part of the project? Can you clarify that? Shotcrete.
Hmm. I'm not sure. I'd have to go back and look at the mixed design. I don't,
Okay.
it was a mixed design that we developed it was more of a strength consideration than
Okay, great. All right. Well, I'm going to say thank you again to Doug Genovan from Schnabel, and I'm going to say thank you to Schnabel for sponsoring this webinar and putting it on for all of our subscribers and providing the complimentary PDH that is now available to you. Again, you have to fill out the survey that I just put in the chat again to get that. Doug, thank you for doing this, for taking the time and spending some time with us and for answering our questions as well. We really do appreciate it.
Sure. Glad to have been part of it. Thanks, Nancy.
All right. Thanks to all of you for joining us and sticking with us today. We appreciate it. We hope that you're enjoying all of our free content at engineeringmanagementinstitute.org. We've got our podcast. We actually have a geotechnical engineering podcast that you could check out, which is hosted by Jared Green. And we do these webinars from time to time. And we have some YouTube channels. We also have a couple of YouTube channels to help you pass the FE and the PE exams. So if you need help with that or you have others, please share that. So thanks again to Doug and Schnabel. We will see everybody in our next webinar. Enjoy the rest of your week. Take care, everyone. Thanks again, Doug.
Thank you. Take care.